1 s orbital, 3 p orbitals and 2 d orbitals intermix, they hybridize and form sp3d2. Only 2 unpaired electrons are there. So what happens? Yes, from 1 electron from here goes to here and 1 electron from here moves to the d orbital. According to valence bond theory, if there are unpaired electrons, the atomic orbitals overlap and they pair up with each other. Atomic orbitals is monocentric and molecular orbitals are polycentric. Hello everyone, this is Ambli Unnikrishnan from the Department of Chemistry, Vidhyaashram Pre-University College, the Temple of Excellence, Mysore. We discussed about, hybridization and the different types of hybridization, right? So, in last session, we discussed on sp, sp2 and sp3 hybridization, right? We discussed about the hybridization involving s and p orbitals, right? So, in today's session, we will be studying about the hybridization of atomic orbitals involving s, p and d orbitals, okay? That is, if we move on to higher molecules, what happens? Yes, the atomic number also increases. So, yes, even d orbitals will be included, right? So, the hybridization involving s, p, d orbitals will be studying in this session, and thereby we will be discussing about the limitations of valence bond theory, and then we will be moving on to the next approach to chemical bonding, that is molecular orbital theory, right? So, beginning with the hybridization involving s, p and d orbitals. So, as you can see here, the first one, dsp2, right? The hybridization type is dsp2. From the name itself, that is from the dsp2 itself, you can understand, yes, 1 d orbital, 1 s orbital and 2 p orbitals, right? They hybridize and form dsp2 hybrid orbital. So, how many number of hybrid orbitals will be formed? Yes, 1d, 1s and 2p. That means 2 plus 1, 3, 3 plus 1, 4. 4 dsp2 hybrid orbitals will be formed. And for such molecules which shows dsp2 hybridization, the geometry will be square planar. Right? Now, moving on to the next one, that is sp3d hybridization. So, what will be sp3d hybridization? That is 1s, 3p orbitals and 1d orbital. Yes, they hybridize and form sp3d hybrid orbitals, right? So, that is 1s, 3p and 1d. Right? As you can see here, 3 plus 1 again it will be 5. Right? Yes, it forms a total of 5 hybrid orbitals, right? And examples for this is PF5, PCl5, right? The PCl5 molecule we will be discussing in detail now, right? Then comes sp3d2, 1 s orbital, 3 p orbitals and 2 d orbitals intermix, they hybridize and form sp3d2. Right. So, a total of how many hybrid orbitals will be formed? 3 plus 2, that is 5 plus 1. A total of 6 hybrid orbitals will be formed. Right. An example for that is BRF5. And then the last one, sp3d2 or d2sp3. In both the cases, as you can see, in sp3d2, 1s, 3p orbitals and 2d orbitals. In the case of d2sp3, yes, it is 2d orbitals, yes, 1s and 3p orbitals. So, a total of 3 plus 2, 5 plus 1, 6 orbitals will be formed here as well. And the example for it is CONH363+, that is a coordination compound, right? Yes, so these are the few hybridizations which is involving d orbitals as well. Right. So, in detail, now we are going to study about the hybridization in PCl5 molecule. Okay. So, in PCl5 molecule, what happens? So, in the ground state, if we consider the valence shell electronic configuration of phosphorus, what it is? Yes, it is 3s2 and 3p3. Right. It is, yes, 3s2, 3p3. That is what is shown here. Yes, and the 3d orbital is free. In this case, in ground state. So, we know that the phosphorus has to bind with 5 chlorine atoms to form PCl5 molecule, right? So how many unpaired electrons are here? Only 3, right? So what happens in the excited state? Yes, one electron from here jumps to the d orbital. Yes, what happens from here? It moves to here. Yes, so now we have 5 unpaired electrons, right? Now what happens? Yes, that is the 3s, 3p and 3d. They hybridize and form the 1s, 3p and 1d orbital, that is sp3d. All of this. So what happens here? They hybridize and form sp3d hybridization, right? 1s and this 3p and this 1d orbital, they undergo hybridization and they form, yes, how many? That is 3, 4, 5. Yes, they form 5 hybrid orbitals. Yes, 1, 2, 3, 4, 5. All of these are, yes, the hybrid orbitals formed. Yes, that is sp3d hybrid orbitals are formed. Now, to these hybrid orbitals, what happens? Yes, they bind with the chlorine atoms. So, as you can see here, now it binds with the 5 chlorine atoms. So, in the diagram also you can see, yes, the phosphorus is in the center, right? And how many hybrid orbitals it is forming? Yes, it is forming 5 sp3d hybrid orbitals, right? So, in this case, even d orbital is taking part in hybridization, one of the d orbitals, right? So, yes, you can see 1, 2, 3, 4 and 5. And now, these 5 sp3d hybrid orbitals, they bind with 1 chlorine atom each. Now, here with 1 chlorine atom, it is forming a bond. Here with 1 chlorine atom, here, here and here. So, finally, we get the PCl5 molecule, right? And what is the shape of this molecule? Yes, it is trigonal bipyramidal, right? Trigonal bipyramidal. It is having trigonal bipyramidal shape. Clear? Now, let's move on to the next one, that is hybridization in SF6 molecule, right? So, in the ground state, the electronic configuration of sulfur is 3s2 and 3p4, right? 3s2 and 3p4. So, we know that in SF6 molecule, right? So, the sulfur has to bind with 6 fluorine atoms, right? So, as you can see here, only 2 unpaired electrons are there. So, what happens? Yes, from 1 electron from here goes to here and 1 electron from here moves to the d orbital. So, as you can see here, there is 1s, 3p and 2 d orbitals that is going to take part in hybridization now. So, what hybridization it will form? It will be sp3d2 hybridization, right? 1s, 3p and 2d orbitals are taking part in hybridization. So, sp3d2 hybridization will be formed and a total of, yes, 6 sp3d2 hybrid orbitals will be formed, and now that 6 hybrid orbitals will form chemical bonds with, yes, each of the fluorine atom, right? So, as you can see, these are the 6 hybrid orbitals, that is sp3d2 hybrid orbitals. Now, each of that will, yes, form a chemical bond with fluorine atom. In the diagram, you can see the sulfur is in the middle, yes, and the sulfur is having how many? 6 sp3d2 hybrid orbitals, right? 1, 2, 3, 4, 5 and 6. Now, the hybrid orbitals will overlap with the atomic orbitals of fluorine atom, right? So, what happens? Now, 1, 2, 3, 4, 5 and 6. It binds with or it forms the bonds with 6 fluorine atoms and you get the shape which is octahedral, right? The shape of such molecules is octahedral, which is having a hybridization sp3d2, right? So, in the case of PCl5, it is sp3d hybridization. Hence, the shape is trigonal bipyramidal. And in the case of SF6 molecule, yes, it is sp3d2 and it forms octahedral shape. So, I hope the 2 examples are clear for you, which is involving d orbitals as well. Right. Now, coming on to the limitations of valence bond theory. Even valence bond theory had its own limitation. So, the first one is it couldn't explain the paramagnetic nature of oxygen. So, in the case of oxygen, we know that the atomic number is 8, right? So, that is 1s2, 2s2 and 2p4. Yes, so the valence shell is having how many electrons? It is having 2 plus 4, that is 6 electrons, right? So how do I represent it? 1s2, 2s2 and 1, 2, 3, 4. 2p4, right? So in this case, we know that yes, 2 unpaired electrons are present in the p orbital. So if it has to, yes, bind with another oxygen atom, what happens? Now these unpaired electron, right? The atomic orbitals will overlap with the other atomic orbitals containing unpaired electrons, and that is how they form the chemical bond. So according to VBT, yes, what it is? Now, if they are forming chemical bonds using the unpaired electrons, what happens? They pair up, right? So, in that case, it should be a diamagnetic molecule. But what happens? So, it was experimentally found out that, yes, oxygen is paramagnetic nature, not diamagnetic. So, that couldn't be explained by the valence bond theory. Next one is it couldn't explain the structure of xenon fluorides. Okay, it couldn't explain the structure of xenon fluorides. Now, let's take the case of xenon. It comes under the noble gas group, right? It is a noble gas. So, we know that they are already stable. If it is already stable, what do we know? They do not form any compounds, or yes, it does not take part in chemical bond formation, right? They already have all the electrons which are paired. Right. So, according to valence bond theory, if there are unpaired electrons, the atomic orbitals overlap and they pair up with each other. So, how can xenon fluoride be formed? Right. Yes. So, it actually is a compound which can be formed, and it couldn't explain the structure of xenon fluorides. Right. So, these were the few limitations of valence bond theory. So, now we are going to study about the next approach to chemical bonding, that is molecular orbital theory. Right. So, till here we studied about VBT, that is valence bond theory. Now, we are going to study about molecular orbital theory. Right. So, as the name suggests, molecular orbital theory. Right. In this molecular orbital theory, we will be studying about the molecular orbitals. Right. So, till here we were studying about atomic orbitals. Right. Yes, we understood that how chemical bonds are formed. Yes, how atoms combine and molecules are formed by the overlapping of atomic orbitals. Right. So, in the case of atoms, we considered atomic orbitals. Right. And we know that inside the atoms, the electrons are present in the atomic orbitals. Right. Same way, in the case of molecules, the electrons will be present in the molecular orbitals. Okay, so what you have to understand in molecular orbital theory is that the two atomic orbitals, they combine and they form molecular orbitals. Now, we know that yes, atoms combine and they undergo chemical bond formation and then molecules are formed. So, what will be present there now? Yes, molecular orbitals will be present there. So, let's understand each of the features of MOT, that is molecular orbital theory. So, before that, yes, it was developed by F. Hunt and R. S. Millikan in the year 1932, right? So, the first one is electrons in molecules are present in molecular orbitals. So, if in atoms it is present in atomic orbitals, yes, in molecules the electrons are present in the molecular orbitals, right? Now, atomic orbitals of comparable energy and proper symmetry combine to form molecular orbitals. So, it is necessary that random atomic orbitals do not combine and form molecular orbitals. Atomic orbitals having comparable energies and proper symmetry only combine and form molecular orbitals, right? Next one, atomic orbitals is monocentric while molecular orbitals is polycentric, right? So, atomic orbitals is monocentric and molecular orbitals are polycentric, right? The next one, number of molecular orbitals formed is equal to number of atomic orbitals combined, and out of which one will be bonding molecular orbital and the other one will be anti-bonding molecular orbital. So, we know that if two atomic orbitals are combining, how many molecular orbitals should be formed? Yes, two molecular orbitals should be formed. That is, the number of atomic orbitals combining will be equal to the number of molecular orbitals formed, right? So, if two atomic orbitals are combining, two molecular orbitals will be formed and one will be bonding molecular orbital and the other one will be anti-bonding molecular orbital, right? And the bonding molecular orbital will be having lower energy and they will be more stable. As the name suggests, bonding molecular orbital. So in the bonding molecular orbital, yes, the probability of finding electron is the maximum, and then hence the bonding molecular orbital will have lower energy and more stability. And the next one is anti-bonding molecular orbital. Yes, it will be having high energy, but they are less stable, right? And the filling of electron follows the same rule as followed in atomic orbitals. So we know that electrons are filled in the atomic orbitals based on the three rules that we had studied: Aufbau principle, Pauli's exclusion principle, and Hund's rule of maximum multiplicity. So in the same way, according to the rules, electrons will be filled in the molecular orbits as well. Yes, I hope it is clear. Now let's try to understand in detail about the molecular orbitals that are found, that is anti-bonding molecular orbital and bonding molecular orbital, right? So we know that yes, matter is particle as well as, it possesses particle as well as wave nature. So if we consider the wave nature, we know that yes, the waves, when they add together, the constructive interference and destructive interference, you know this about the waves, right? So as it is having particle as well as wave nature, yes, in the case of wave nature, if we are considering, yes, constructive and destructive interference are possible, right? So we studied that the function psi is used to represent the atomic orbitals, right? So if I am consider the two atomic orbitals of atom A and atom B as psi A and psi B, they are two atomic orbitals. Yes, the wave function or the wave is shown here, as you can see. So when the two waves are added, what happens? Yes, the overall one is psi A plus psi B. Now this psi A plus psi B represents the bonding molecular orbital. Now the same way, if the waves are subtracted from each other, yes, we get psi A minus psi B, which is the anti-bonding molecular orbital, right? So this one which is formed, it is the bonding molecular orbital, and this is anti-bonding molecular orbital. So this corresponds to psi A plus psi B, and this corresponds to psi A minus psi B. Right, I hope it is clear. The psi A and psi B represents the different atomic orbitals of A and B atom. Clear? So as you can see here, when these two oneness orbitals I am considering, if I am considering two oneness orbital, if these two atomic orbitals combine, yes, how many molecular orbitals will be formed? Two molecular orbitals will be formed, right? So if this is psi A and this is psi B, yes, if the constructive interference take place between them, that's psi A plus psi B, yes, then bonding molecular orbital is formed. Yes, that is written there, right? And now in the case where there is a subtraction of the waves taking place, that is destructive interference, yes, anti-bonding molecular orbital will be present. Yes, so that is written as sigma and sigma star. As you can see, sigma and sigma star. Right? Yes. So the bonding molecular orbital will be represented as sigma, anti-bonding will be represented as sigma star. So the psi function that we were talking about, actually it is used to represent the atomic orbitals, right? The wave function psi. Yes. So the value for it is actually to be derived from Schrodinger wave equation. Hence it is very difficult to calculate it for multi-electronic species. Yes. A assumption method was used to understand about the linear combination of this atomic orbitals, which is known as linear combination of atomic orbitals or LCAO. And there are few conditions for this LCAO. Let's go one by one. Yes, the first one is the combining atomic orbitals must have equal energy. Yes, the atomic orbitals which are combining to form molecular orbitals, they must have equal energy. Second one, atomic orbitals must have same symmetry about molecular axis. So they must have equal energy as well as same symmetry. And then the combining atomic orbitals must overlap to the maximum extent. So that means if their extent of overlapping is more, that means more strong bond will be formed, right? Yes, we know that. Yes, greater the extent of overlapping, greater will be the strength of the bond. We have studied that. So the combining atomic orbitals must overlap to a great extent for it to form a strong bond. Clear? Now moving on to the different types of molecular orbitals. Yes, there are two types of molecular orbitals, that is sigma molecular orbital and pi molecular orbital. Now the speciality of sigma molecular orbital is it is symmetric around the bond axis. As you can see here, yes, it is symmetric along the bond axis. On either side, it will be symmetric. But in the case of pi molecular orbital, it won't be symmetric along the bond axis. Yes, that is about sigma and pi molecular orbital. So as you can see here, in this case, two 1s orbitals are combining. It is forming one bonding molecular orbital and one anti-bonding molecular orbital, right? So the bonding molecular orbital is represented as sigma 1s and the anti-bonding molecular orbital is represented as sigma star 1s. Right? So, in the case of sigma molecular orbital that is formed, it will be symmetric about the bond axis. So, that is the two types of molecular orbitals. So, now you can see here in this case how the molecular orbital diagram is drawn, you can see. So, this 1s orbital you can see it is of one atom and this 1s orbital is of another atom. Right? And then these two atomic orbitals combine and they form two molecular orbitals, right? So, one will be sigma 1s and the other one will be sigma star 1s, right? Yes, so these two atomic orbitals, that is 1s and 1s of different atoms, yes, they combine and form the molecular orbital sigma 1s and sigma star 1s. So, we studied that bonding molecular orbital is having less energy and high stability, right? So, that is why sigma 1s, that is a BMO, bonding molecular orbital, is placed below and sigma star 1s is placed above because it is having high energy and less stability. Clear? Yes. So, now let's move on to the energy level diagram for molecular orbitals. We are going to see how we can represent the molecular orbitals using molecular orbital diagram, right? So, before that, we need to be knowing the increasing order in which the electrons must be filled in the different molecular orbitals. Say, yes, so for oxygen and fluorine molecules, yes, this order should be maintained. That is sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, then comes sigma 2pz and then pi 2px is equal to pi 2py, then pi star 2px is equal to pi star 2py and then sigma star 2pz. So, from here you can see that, yes, in p orbital we know that there is px, py and pz orbital, right? So, the px and py, they form pi molecular orbital and the pz, yes, the pz forms the, yes, sigma molecular orbital. I hope it is clear. So, this is the order in the case of O2 and F2 molecule, right? Now, coming on to the other molecules, other than O2 and F2 molecules, the order is a little bit different, right? So, it is sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, then instead of sigma 2pz, pi 2px is equal to pi 2py comes and then sigma 2pz, then pi star 2px is equal to pi star 2py and then sigma star 2pz. So, wherever you are able to see the star sign, it represents, yes, anti-bonding molecular orbital. Yes, and wherever you cannot see that, that is bonding molecular orbital. Yes, so let's see the molecular orbital diagram so you will get a better idea of it. Yes, so in this case, as you can see, it is for oxygen and fluorine molecule, how it is represented. So, let's take the example of oxygen molecule itself, right? Yes, so in the case of oxygen molecule, we know that two atoms of oxygen are there. So, one atom of oxygen, from there 1s orbital and the other oxygen atom 1s orbital, right? Now, they combine, yes, the two atomic orbitals combine and they form two molecular orbitals, right? That is sigma 1s and sigma star 1s. Right, then sigma 2s and sigma star 2s is formed from the 2s orbitals, right? Then sigma 2pz, then pi 2px is equal to pi 2py, then pi star 2px is equal to pi star 2py and the highest energy is for sigma 2pz, which is coming from the combining of atomic orbitals 2p and 2p of the oxygen atoms. So, let's try to fill it in the case of oxygen molecule. Yes, we know that in oxygen atom, how many electrons are there? Yes, in oxygen atom, a total of 8 electrons are present, right? So, in the case of oxygen molecule, yes, a total of 16 electrons will be there. So, we know that in one oxygen atom, a total of, yes, 8 electrons are there. So, in here, 2, in 2s2, that is 1s2, 2s2 and 2p4 is the electronic configuration, right? We know that 1s2, 2s2, 2p4. Now, coming on to the other oxygen atom also, it is 1s2, 2s2 and 1, 2, 3, 4. Right? Now what happens? Yes, these two atomic orbitals, they combine and form two molecular orbitals. So first it fills in sigma 1s, then sigma star 1s, right? Then sigma 2s, sigma star 2s. A total of 16 electrons is now to be filled. So 1, 2, 3, 4, 5, 6, 7, 8. Then it fills sigma 2pz, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then it fills this 11, 12, 13, 14 and it singly fills. Right. So we know that in the atomic orbitals, first the atomic orbitals having same energy, they must be singly occupied, then only they will be starting to pair up, right? So hence it will be singly paired. So from this what you can understand? Even you can understand that the oxygen molecule is not diamagnetic, it is paramagnetic, right? So in the case of VBT, it couldn't be explained, but the using molecular orbital theory, it is able to explain that yes, even the oxygen molecule is paramagnetic because yes, you can see there are unpaired electrons which is present. So I hope it is clear. Now moving on to the yes, molecular orbital diagram for other than oxygen and fluorine molecule. So let's see here. In this case, yes, till here it is the same and here it changes. Yes, in here it was sigma 2pz first, then pi 2px is equal to pi 2py. Here pi 2px is equal to pi 2py, then sigma 2pz, then 2px is equal to pi star 2py and then finally sigma star 2pz. Yes, so let's take the example of C2 molecule in this case. Okay, so we know that in a carbon atom, a total of 6 electrons are present. So in carbon molecule, a total of 12 electrons will be present, right? So yes, in each carbon atom, a total of 6 electrons are there. Yes, 1s2, 2s2 and 2p2 is the electronic configuration of carbon, right? Now here also it is 1s2, 2s2, 2p2. Yes, from two carbon atoms. Now we know that 1s orbitals of both the carbon atoms, they combine and form molecular orbitals which is sigma 1s and sigma star 1s. Right. So now a total of 12 electrons are needed to be filled. Yes. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and 11, 12. Yes. So now a total of 12 electrons are being filled. Right. So now from there what you can understand? Yes, C2 molecule is diamagnetic, not paramagnetic, right? There are no unpaired electrons in this case. So I hope for yes, oxygen and fluorine molecule, how the molecular orbital diagram can be made, and for the other molecules, how it is. I hope it is clear for you. The difference between both of them is clear for you. Yes, there is a small change in the yes, energies of sigma 2pz and pi 2px is equal to pi 2py. Here sigma 2ps comes in with less energy and here it is pi 2px is equal to pi 2py. So I hope you are clear with how to represent the molecular orbital diagram. So in the next session, we will be studying about the electronic configuration and molecular behavior and then bonding in some homonuclear diatomic molecules. We will be studying in detail about the bonding present in some diatomic molecules. Yes, and then finally we will study about hydrogen bonding, which will come to an end to this chapter. Yes, so I hope what and all we have discussed in this session is clear for you. So that's all for today. Thank you.